Hello everyone, welcome to my channel Chemical Engineering Knowledge. In the previous lecture we have discussed about the overall heat transfer coefficient, the Pauling factor. In this lecture we will discuss about the analysis of heat exchangers. So in the analysis of heat exchanger we usually use two methods to design a heat exchanger. One is the LMTD method, the log mean temperature difference method, and the second one is the NTU method. The NTU method is the number of transfer unit method. So in these two methods we are using to design a heat exchanger. This is a problem. This problem is related to the LMTD method. So in this problem we will design a heat exchanger and we will use the LMTD method, which is the log mean temperature difference method. So the problem is we are going to heat a cold water in a counter current flow heat exchanger. So we will use a counter current flow heat exchanger and we will heat a cold water with the help of hot geothermal water. So the hot geothermal water will give its heat to the cold water, and the temperature of the cold water in the counter current flow heat exchanger will decrease. So the temperature of the cold water in the counter current flow heat exchanger will increase and the temperature of the hot water will decrease. Now the given information are is follow. The inlet temperature of the cold water is 20 degrees centigrade. The mass flow rate of the cold water is 1.2 kg per second, and the outlet temperature of the cold water is 80 degrees centigrade. The cold water is flowing in the tube side, while the hot water is flowing in the shell side of the shell and tube heat exchanger. The inlet temperature of the hot geothermal water is 160 degrees centigrade, and the mass flow rate of the hot geothermal water is 2 kg per second. Now there is a question. Similarly, the overall heat transfer coefficient is 640 watt per square meter into Kelvin, and the diameter of the tube is 1.5 centimeter. This is a counter current flow shell and tube heat exchanger. The cold water, this is the cold water. The temperature of the cold water is TCI. The inlet temperature of the cold water is 20 degrees centigrade, and the mass flow rate of the cold water is 1.2 kg per second. The cold water is flowing inside the tube, while the hot water is flowing in the shell side. The hot water is flowing in the shell side, of the shell and tube heat exchanger. So this is the hot water. The inlet temperature of the hot water is 160 degrees centigrade, and the mass flow rate of the hot water is 2 kg per second. The inlet temperature of the cold water is 20 degrees centigrade, and the outlet temperature of the cold water is 80 degrees centigrade. Now there is a question that what will be the length of the shell and tube heat exchanger. So what will be the length of shell and tube heat exchanger? So in this method we will use the LMTD method. We can also use the NTU method, but in this lecture we will use the LMTD method to design the heat exchanger and to determine the length of the shell and tube heat exchanger. So first of all we will write a general heat balance equation, which is nothing. We will assume that the kinetic energy and the potential energy, in the heat analysis and in the heat equation, the kinetic energy and the potential energy will be negligible, so these will be zero. And there we will write the general heat balance equation, which is heat rate is equal to the overall heat transfer coefficient into the surface area of the heat exchanger and to the temperature difference, the log mean temperature difference. Now the log mean temperature difference, but our question is what will be the length of the heat exchanger. So first of all we will determine the heat rate, and we will determine the heat rate. The overall heat transfer coefficient is given to us, and this temperature is also unknown to us. Some temperature is given to us, but some temperature is unknown to us. So so first of all we will determine this heat rate, then we will this is given to us, then we will determine this one, the Lagrange temperature difference, and from these three quantities we will determine the surface area of the heat exchanger, and then from the surface area of the heat exchanger we will determine the length of the heat exchanger by using the formula that surface area is nothing but it is the pi dl. So the diameter of the tube is given to us, and the surface area will be also given to us. So we will determine the length of the heat exchanger, or the length of the tube. So the length of the tube is equal to the length of the heat exchanger, because the length of the tube is equal to the length of the shell in this case. So first of all we will determine the heat rate, this Q rate. So we know that Q is equal to mass flow rate into specific heat Cp into delta T. So when the cold water is flowing, inside the tube, so this is the cold water which is flowing inside the tube. The mass flow rate is this one, and this is the temperature T1 Tci, and the inlet temperature of the cold water, and this is the outlet temperature of the cold water. So the heat, when the cold water is flowing inside the tube, then this geothermal hot water will give its heat to the cold water. So will give its heat to the cold water. So the heat gained by the cold water inside the tube will be given by mass flow rate of the cold water, the heat capacity of the cold water, heat capacity of the cold water, and the heat capacity of the cold water into the temperature difference. So the specific heat of the cold water, this is the mass flow rate of the cold water, this is the specific heat of the cold water. So, and this is the temperature difference. So now the mass flow rate of the cold water is given to us. The mass flow rate of the cold water is from this 1.2 kilogram per second. So 1.2 kilogram per second. 1.2 kilogram per second. Similarly, the mass flow rate of the 1.2 kilogram per second, and the specific heat of the cold water is how can we determine the specific heat of cold water? So the specific heat of cold water can be determined from various tables at the average temperature. For example, we will add this temperature 20 degree plus 80 degree. This temperature, it will give us 100 degree divided by 2. So at about 50 degrees centigrade, the specific heat of cold water will be 4.18 kilojoule per kilogram into Kelvin. So at the average temperature 20 plus 80 divided by 2, which is 50 degrees centigrade. So at 50 degrees centigrade, the specific heat of the cold water will be 4.18. You can obtain it from literature or from graphs or from other tables given in various books. So 4.18 kilojoule per kilogram into Kelvin. This is the specific heat. This is the specific heat of cold water. Now this is the temperature difference. Now this temperature difference is nothing but the outlet temperature of the tube, outlet temperature minus inlet temperature, 80 minus 20. So 80 minus 20, which is again 60. So this is the 60 degree centigrade. 60 degree centigrade. Now this kilogram cancels with kilogram, and this is the second. So the kilojoule. Now the temperature 1 Kelvin. By conversion, 1 Kelvin is equal to 1 degree centigrade. This is also cancelled with this, and this is the kilojoule. 1.2 multiplied by, if we simplify this, then it will be 1.2 multiplied by 4.18 multiplied by 60. So it will, the kilojoule per second, it will give us the a kilowatt. So it will give us the kilowatt, 301 kilowatt. 301 kilowatt. So this 301 kilowatt is the energy which is given by the hot geothermal fluid to the cold water. So this Q0 is nothing but the energy which is given by the hot geothermal fluid to the cold water which are flowing inside the tube. So this Q0 is the energy given by the hot geothermal fluid to the cold water. Now, what will be the when the hot geothermal fluid gives its energy to the cold water, then what will be the temperature, the outside temperature of the hot geothermal fluid? So again, we know that the energy given by hot geothermal fluid to the cold water will be equal to the energy gained by the cold water. So the energy gained by the cold water will be equal to the energy given by the hot geothermal fluid. So the energy gained by the cold water in this case is 301 kilowatt, or the energy given by the hot geothermal fluid is also equal to 301 kilowatt. So the energy given by the hot geothermal fluid is Q0, which is 301 kilowatt, and by energy balance Q is equal to mass flow rate of the hot geothermal fluid which are flowing inside the shell, and the heat capacity and the specific heat of the hot fluid, and the temperature difference of the hot fluid. So the mass flow rate of the hot fluid is given to us. It is 2 kg per second. This one, 2 kg per second. This one, 2 kg per second. So it is 2 kg per second. 2 kg per second. Now the specific heat of the hot fluid. So the specific heat of the hot fluid will be obtained from the average temperature. For example, 160. So the specific heat 160 and this temperature divided by 2, but this temperature is unknown to us. So at this time the specific heat of the hot fluid will be obtained from table at this temperature 160 degrees centigrade. So at 160 degrees centigrade we will obtain the specific heat, the heat capacity, the specific heat, at 160 degrees centigrade we will obtain the specific heat of the hot fluid from various table or graph. Or you can also obtain the you can also assume this temperature. Suppose this is 160, so you can consider it 100 degree centigrade or 120 degree centigrade. So suppose I assume at 100 degree centigrade and this is 160, so this will be 260 degree centigrade and divided by 2, it will be 130. So the heat capacity, so the specific heat of the hot fluid will be obtained at 130 degree centigrade from various table or various literature books. So the heat capacity, the specific heat of the hot fluid which we have obtained from literature is 4.31. So 4.31 kilojoule per kilogram into Kelvin, and this is the temperature difference. So this temperature difference is unknown to us. The inlet temperature of the hot fluid is known to us, which is 160. This is 160 degree centigrade, but the outlet temperature of hot fluid is unknown to us. So and this Q is known to us. This is the heat given by the hot fluid. So the heat given by the hot fluid to the cold fluid. So from this equation this equation can further simplify. Q is equal to mass flow rate of the hot fluid, Cph. This is the inlet temperature of the hot fluid, outlet temperature of the hot fluid. So from this relation we can obtain the outlet temperature of the hot fluid, like Q naught M, mass flow rate of the hot fluid, Cph is equal to inlet temperature of the hot fluid, but we are going to obtain the outlet temperature. So we are going to obtain the outlet temperature of the hot fluid. So the outlet temperature of the hot fluid, in this case, this is inlet, this is the outlet. So the outlet temperature can be obtained by hot fluid inlet temperature minus heat given by the hot fluid, mass flow rate of the hot fluid, and Cph. So from this relation, this temperature is given to us, this is given to us, this is given to us, this is given to us. So we can obtain the outlet temperature of the hot fluid. So putting the value, the outlet temperature of the hot fluid is the inlet temperature of the hot fluid is 160 degrees centigrade, and the heat given by the hot fluid is 301 kilowatt, and the mass flow rate of the hot fluid is 2 kilogram per second, and the Cph is 4.31 kilojoule per kilogram into Kelvin. So this is the MCP. So this is the MCP. Now we can further simplify it. So after simplification, the hot fluid outlet temperature will be 125 degrees centigrade. So 125 degree centigrade. So in this case, the inlet and outlet temperature of the hot and cold fluid are obtained from various relations. So the hot fluid, so this is 125. This is 125 degrees centigrade. The hot fluid outlet temperature. Now the hot fluid outlet temperature. Now the hot fluid temperature is obtained. Now we will obtain the log mean temperature difference. This is our log mean temperature difference. Now the log mean temperature difference is nothing. The log mean temperature difference is nothing but it is delta T1 minus delta T2 divided by ln delta T1 divided by delta T2. So the delta T1 and delta T2. Now the delta T1 is nothing but it is the difference between the delta T1 is nothing but it is the difference between the hot fluid inlet temperature and the cold fluid outlet temperature. So the difference between this hot fluid inlet and the cold fluid outlet is given by delta T1, and the difference between the cold fluid inlet and the hot fluid outlet, this Tci and Th naught. So the difference between the Thi minus Tc naught, delta T1, this one, this, and the difference between hot fluid outlet, the hot fluid outlet and the cold fluid inlet is given by delta T2. This is delta T2. So the delta T1 is the hot fluid inlet temperature, cold fluid outlet temperature. Delta T2 is the hot fluid outlet temperature minus the cold fluid inlet temperature. From this, the hot fluid inlet temperature is 160 degrees centigrade, and the cold fluid outlet temperature is 80 degrees centigrade. Similarly, the hot fluid outlet temperature is 125 degrees centigrade, and the cold fluid inlet temperature is 20 degrees centigrade. So, from simplification of this, delta T1 will be equal to 80. This will be equal to 80 degrees centigrade, and delta T2 will be equal to 125 minus 20. So it will be equal to 105 degrees centigrade. So fitting the log mean temperature difference in this case will be equal to delta T1 is equal to 80 degree minus delta T2 is equal to 105 ln 80 divided by 105. So this is the after simplification we will get the log mean temperature difference, which is 91.9 degrees centigrade. 91.9 degrees centigrade. So the log mean temperature difference will be this one. Now, in the start of this lecture, we have written the formula that the overall heat rate is equal to the overall heat transfer coefficient and the surface area of the heat exchanger and to the log mean temperature difference. So the log mean temperature difference in this case is obtained to be 91.9 degrees centigrade. And the overall heat transfer coefficient is given to us, and the heat gain or heat loss by the cold or hot fluid is also given to us. So the heat gain by the cold fluid or the heat loss by the cold fluid is given, and its value is 301 kilowatt. The overall heat transfer coefficient value is also given to us. So the value of the overall heat transfer coefficient is 640 watt per meter square into Kelvin. And the log mean temperature difference value is also given to us, 91.9 degrees centigrade. And this area is unknown to us, so we can obtain this surface area of the heat exchanger from this relation. So this is, we can further simplify 301 kilowatt is equal to 640 watt per meter square into Kelvin, and 91.9 degrees centigrade into the surface area of the heat exchanger. So after simplification and after unit conversion, the surface area of the heat exchanger come out to be 5.12 meters square. 5.12 meters square. 5.12 meters square. Or we can also make conversion of this. So like this 1000 watt is equal to 1 kilowatt. So this watt cancel with this watt, and this kilowatt cancel with this kilowatt, and we also know that degree centigrade is equal to Kelvin, so this will cancel with this one. So this area will come to this side, and after simplification we will get this area. So the area of the heat exchanger is obtained. Now this is the area. Now we know that the surface area of the heat exchanger is nothing but pi d diameter. The surface area of the heat exchanger, or the surface area of the tube, is pi into the diameter of the tube into the length of the tube. The diameter of the tube is given to us. That is 1.5 centimeter. So, and the surface area of the tube is obtained 5.12 square meter, and the pi is 3.14, and the diameter is 1.5 centimeter, and the length. So from this we can obtain the length of the heat exchanger. So from this we can obtain the length of the heat exchanger, like surface area is equal to 5dl, and this is the 5.12 square meter is equal to 3.14 and 1.5 centimeter into length. So 1.2 square meter, 3.14, 1.5 centimeter. So we know that 100 centimeter is equal to 1 meter. So the centimeter cancel. 100 centimeter is equal to 1 meter. Centimeter cancel with centimeter. Meter cancel with this 1 meter. So it will again 5.12 multiplied by 100 divided by 3.14 multiplied by 1.5. This is meter, the length. So the length of the tube of the shell and tube heat exchanger come out to be 109 meter. 109 meter. Again, this is very long tube for the shell and tube heat exchanger. So in order to overcome this problem, we should use multi-pass shell and tube heat exchanger. So multi-pass shell and tube heat exchanger. So for example, this is a shell. So we can use multi-pass of the tube in shell and tube heat exchanger to reduce this long length of the tube in the heat exchanger. So thank you very much for your attention. If you are new to the channel, please like and subscribe to my channel.